In topic 8.9, we start to get into volumes of revolution. And we're kicking it off here with disk method, where we're revolving around either the x-axis or the y-axis specifically. So let's look at x-axis rotation. Remember that when we have x-axis rotation, that means that we are revolving here around the x-axis, and we're creating sort of this horizontal figure with its center around the x-axis. When that's the case, we're going to take slices that are perpendicular to the x-axis, and when we take a slice like that, it's going to create a disk. Well, remember that a disk is a circle, basically, and the area of a circle is pi r squared. Well, when we think about the radius of this disk, what we see here is that we have this radius from the top to the x-axis. Well, the top of the object here is defined by this function f of x. That's this curve along the top of the object, the curve that we're rotating around the x-axis. And then the bottom of the radius is defined by the x-axis. So the radius, we could say, is equal to f of x minus 0, where 0 is the line y equals 0, the x-axis. And of course, that's just equal to f of x. So our radius is f of x, which means the area of the circle, the area of the disk, is pi times f of x quantity squared. And that's what we see up here in our volume formula. Remember that when we use disk method, the integral we're taking, we can really just think about as area times width. That area times width gives us the volume of one cross-section, and then integrating means that we're adding up the volumes of all the cross-sections over a particular interval to get the volume of the entire figure. So the area here is given by pi times f of x quantity squared. So this here in blue is the area of this disk. And then if we want to give that disk a little bit of width to make it an infinitely thin slice, then we just think about adding a little bit of width here to that disk, and that width is delta x. Now we have a three-dimensional disk that has just a tiny bit of width to it. And so if we multiply this here by delta x, this gives us now the volume of one of the cross sections, of one of the disks. And so in order to find the volume of the entire figure, we integrate this value. And so you can see here the integral of pi times f of x quantity squared. Our delta x becomes dx. And we're simply integrating over the interval a to b here, whichever interval defines the figure. So if the edge of the figure here is at 0, and let's say b is 5, we'd be integrating over the interval 0 to 5. And that's how we set up our integral for the volume of rotation with disk method when we're rotating around the x-axis. And we have a very similar process when we rotate around the y-axis. So in this case, we have a curve. So our curve is, let's say, this curve right here along the edge of this figure. So that is our curve. We'll call it f of y. That would be some curve given to us as x equals and then some function in terms of y. We're asked to rotate that around the y-axis, and when we do, it's going to create a figure like this with some kind of volume. We'll be using cross-sections then that are perpendicular to the y-axis. And so when we slice this perpendicular to the y-axis, we get this horizontal disk. And again, the area of that disk is given by pi r squared, but our radius is defined by f of y minus 0, or just f of y. So the area is again given as pi times f of y quantity squared. And then when we add a little bit of width to this disk, we give it a little bit of height like this, and that height we say is delta y. We multiply this by delta y. That gives us a little disk of volume, but then we want to add up all of the disks that make up this entire volume, and so we'll say that we're adding these up between y equals c and y equals d. And so when we integrate, we see that the pi f of y quantity squared becomes pi f of y quantity squared, the delta y becomes dy, and our limits of integration are from y equals c to y equals d to add up all these disks at these different levels all the way from c to d. topic 810, we're again looking at volumes of revolution with disk method, but we're revolving around other axes of revolution. So let's focus in first here on the left-hand side. Remember that when we use disk method, it's all about this integral here. This is really what we want to remember, the integral of area times width. And we want to think about this area times width as relating to the cross-section of the figure, of the three-dimensional figure that we're creating when we rotate around the axis of revolution. So let's imagine here that we have this scenario. We have a function f of x, and we have this horizontal axis of rotation y equals k. So this is the line y equals k, and we're rotating around this axis. When we do that, of course, what we're going to get f of x here to look like on the other side is this line like this after the rotation. Now we have a cone that's sort of laying on its side. It's a three-dimensional object with volume. And so now we want to start thinking about cross-sections. Well, remember, cross-sections are always going to be perpendicular to our axis of rotation. So because our axis of rotation is horizontal, our cross-sections need to be vertical. So if we think here about a cross-section like this, that cross-section is going to be a disk. So if we think about a disk that looks like this, so that disk is a cross-section, and we need to find the area of that cross-section. Well, the area of a disk is pi r squared. That's the area of a circle. So what's the radius? The radius is this value right here. It's defined between f of x and k. So we can either define the radius as k minus f of x, or we can say, or as f of x minus k. So we plug that in here and we say that the area of the disk is pi times k minus f of x quantity squared. That is the area of this whole disk here. And we see that up here as the area. Then all we want to do is give this disk a little bit of width. So we add a little bit of width to this disk to make it a three-dimensional volume, a very thin slice of volume. And that width we can indicate as delta x. So we multiply here by delta x in order to get the volume of this infinitely thin slice. And then in order to add up all the cross sections to come up with this volume, we integrate this value. And of course we see the pi times k minus f of x quantity squared, that's our area here. The delta x becomes dx, and then we simply integrate over the interval here from x equals a, so at this value here, to x equals b at this value here. And that's going to add up all of our cross sections that make up this volume here. We add up the cross sections between x equals a and x equals b, and that's our integral. Or if we want to set up the opposite situation where we have a vertical axis of rotation. So in this case, we're rotating around the line x equals k. We have this vertical axis of rotation, so we're going this way. When we rotate this function f of y, what we get is a cone standing on its base that looks like this. Of course, we immediately want to think about the cross section. And when we do, that cross section is going to look like this. It's going to be a disk that is perpendicular to the axis of rotation, so perpendicular to the line x equals k, or parallel to the x-axis. We know that that's a circle, and so of course the area of a circle is pi r squared, so all we have to worry about is the radius, and that radius is simply the distance between the axis of rotation and the edge of the circle. That's our radius. So the radius becomes k, the axis of rotation, minus f of y. And similarly here, we could say f of y minus k, and we'd still come out with the same value. And the reason is because either way, we're finding the distance between the two, just like over here. We're finding the distance between these two things. One's going to come out as a positive value, the other one's going to come out as a negative value, but then we're going to square it here in our equation, so it doesn't matter, which is going to make that distance positive either way. So it doesn't matter which setup we use, k minus f of y or f of y minus k, in the same way that over here we could use k minus f of x or f of x minus k. So we have our radius, we plug that into our area formula, and then our area becomes pi times the radius, k minus f of y, quantity squared. That's now the area, this whole thing in blue. If we want to give this disk a little bit of volume, a little bit of width, or a little bit of height, we have that volume piece there, we give it that height. That height is delta y, and so we multiply this over here by delta y. And then in order to add up all of these cross sections that we would take from the bottom to the top here, we just integrate this. And so you see everything being integrated. The delta y becomes dy, and we're integrating over y equals c to this point up here, y equals d. And so our limits of integration are y equals c to y equals d. And so that's how we set up an integral to calculate the volume using disk method when we're rotating around a vertical axis. In topic 811, we look at washer method, and in this particular topic, we're looking only at revolution around the x or y axis specifically. So here, let's look at revolution around the x-axis. So y equals 0, or the x-axis, is our axis of revolution, so we're revolving this way. And let's say here that we've been given this curve, we'll call this one f of x, and this curve g of x. And so when we revolve those around the x-axis, we get something that looks like this. Just like with disk method, when we have washer method, you still want to go back to the integral of area times width. Area is going to be given by the area of the disks, and width is going to be given by this differential value dx. And the whole idea here is, think about this as two separate disk method problems, right? Because if we imagine for a second that g of x isn't here, and we just have f of x, it creates this full solid here, and we can find the volume when we rotate f of x around the x-axis as a disk method problem. We would just have this first half here, pi times f of x quantity squared, because f of x is the radius, and then we would have the dx. So this second part here, where we subtract out pi times g of x quantity squared, this is just subtracting out this center part, because this volume of revolution is really going to be given by this here. This is the volume. This is our solid figure here. And it just has this big hole in the middle. This middle part here is hollowed out. So we still take a cross section that is perpendicular to our axis of rotation. It's perpendicular to the x-axis. And we look at f of x first. We say that the radius is given by f of x minus 0. So the radius is just f of x, which means that the area of a cross section of f of x is pi times the quantity f of x squared. That's the area of a cross section of f of x. But then we want to subtract out from that the area of a cross section of g of x. So if we look here at g of x, the radius of this cross section is g of x minus 0, or just g of x. And so the area of that cross section is this pi times g of x quantity squared. So by subtracting one from the other, we're just ending up with this width right here as our radius, the difference between f of x and g of x. So that becomes our radius. This whole thing here is the area of that radius revolved around the x-axis. And then we just want to give that cross section a little bit of width. So this little bit of width here, which we indicate with a delta x. And so we multiply our area by our width delta x, and then we integrate that over the interval here given by x equals a to x equals b, whatever our limits of integration are. And that's how we set up our integral. And the same is true for a vertical axis of rotation. So let's say in this case that we are revolving around the y-axis, or the line x equals 0. So we're revolving this way. Let's say that we have here this outer curve, f of y, and our inner curve here, g of y. And so again, looking at the outer radius, let's pretend that g of y does not exist, and we just have f of y, and this is a disk method problem around the y-axis. That's how we get the pi times f of y quantity squared. But then in order to just get this value right here, we have to subtract out the radius given by g of y. So we have to subtract out this area right here from that disk. And that area is given by pi times g of y quantity squared. We subtract that out. That just gives us the yellow value. So that's our area here of one cross section. And then we give that cross section a little bit of height, a little bit of width. We make it a volume, and we call that delta y. And so then our area we have here in blue, the width or the height we have as delta y, but when we integrate that becomes dy. And then we're integrating over limits of integration from y equals c up here to y equals d. And so we have the bounds on our integral. So with all of these kinds of problems, you just want to work through this process of find the area, then turn that cross-section into a little volume by giving it some width, and then add up all those volumes by integrating over a particular interval. So in topic 812, we're talking about washer method, but we're revolving around axes of revolution other than the x-axis or the y-axis. But of course, as with all of these volumes of revolution problems, we're still focused on this integral here, the integral of area times width. The only tricky part is figuring out this area. We already know width is dx or dy. So let's say we have the horizontal axis of revolution y equals k. So we're revolving this way. And when we do that, what we get is g of x and f of x to appear here on the other side of the axis. So that could be g of x there, and this could be f of x here, something like this. So we have now this volume, this three-dimensional object with volume. And remember, we always want to look at the area of the cross-section of the outer curve first, the curve that's further away from the axis of revolution. In our case, that's f of x. So if we think about a cross-section of f of x, we could just find that using disk method. And what we see is that the disk is going to be a circle, so the area is pi r squared. The only part we have to find is the radius, and the radius is going to be given by the difference between the axis of revolution and the curve. So we have k minus f of x. So we have pi times r squared. Pi r squared, that gives us the area of this disk, this cross-section for f of x. But then, as you know, we have to subtract out the area given by the disk for g of x. So if we think about using disk method on g of x, we're going to have this cross-section here. The area of that disk is going to be pi times k minus g of x quantity squared. And so because all we want is this area right here, the difference between the two, the difference between f of x and g of x, we want to subtract out the g of x part from the f of x part. And so that's why you see that we're taking the difference of the area of the f of x disk and the area of the g of x disk. That gives us the portion here in yellow as an area. And so that's our area portion, this area portion here. And then we want to multiply that by a width. So we just give this a little bit of width here, and that width is delta x. And so then when we integrate to add up all of these cross sections, so we're thinking about adding up all of these cross sections throughout this whole volume here, we're integrating over x equals a to this point here, x equals b. We already have our area expression, and then the width, dx, comes directly from this delta x. And we know that the same thing happens when we rotate around a vertical axis of revolution. So let's say we're rotating around the line x equals k. That means that our rotation is going to look something like this around the axis. And so if we have curves g of y and f of y, and then we rotate them around this axis, this is what they look like on the other side. And again, we're focused on first using basically disk method to find the area of a cross-section that'll define f of y. And so we know that that area using disk method is given by area equals pi r squared, the area of a circle, or the area of the disk. The radius is simply the difference between that curve and the axis there. So we could find that radius by saying k minus f of y. That's what we see here, k minus f of y. So the radius is k minus f of y. And so the area then is pi times k minus f of y quantity squared. That's the area for the entire cross-section between the edges here of f of y. But then we need to subtract out this area here, the disk that defines g of y. And so in order to get the radius of that disk, we take k minus g of y. And so the area of the cross-section that defines g of y is this here. So when we subtract this inner disk from the outer disk, we get the area just between these two curves, which is what we want. We want the area between these two curves only. And so that area is given by this whole expression here. And so we just give that little piece of area a little bit of height. Well, that height is delta y here. And so we see that height or that width as dy here in our integral. So when we want to add up all of these cross sections, we're adding up all these cross sections like this, these horizontal cross sections, and we say the area times the width, and then we want to integrate here between y equals c and up here y equals d, whatever our limits of integration happen to be depending on our curves. And this here is going to give us the volume of our figure when we're revolving around a vertical axis, x equals k.